Thank you for sharing. Hello everyone. Welcome. And today we're talking about mathematical modeling. Um, it's a topic that I know enough about, but not an expert in it. But I think I know enough to it about. Okay, so we will start with the definition. What's mathematical modeling? And it's basically taking a real system and representing in terms of mathematical equations. It's that straightforward. Okay, so who uses mathematical modeling? Well, I think an easier question would be who doesn't use mathematical modeling, because virtually everyone does, or every field it's used. You know, mathematics, stats, physics, chemistry, engineering, of course, you name it. Economy, finance, so on and so forth. Okay? So we're going to start with an example of mathematical applications. So as Brother Rashad said, I work for this company called Space Foods, and one of our products is potato salad, and of course one of the main ingredients is potatoes itself. So this is the cooling process. So it's cooked in a blender, which is here, at about 100 degrees. It's then immersed in water, chilled water, which cools down to about 25 degrees. And then finally, it's put in a chiller that's at 4 degrees. Okay? Now, we want to model this process so we can optimize the process. So one of the if you can optimize this process, for example, then that means we can minimize the water loss, and we can also predict how long it will take the product to go to the desired temperature.
Is this okay? Would you be taking questions along there, or we have to wait till the end? I think it would be better because something came to my mind. What exactly you mean by optimization here? Like, okay. I just need to.
Right. Okay. So optimization refers to getting into the best condition. Okay, getting the best out of a system. Okay, so for example, you got a cooling process here, right? So if you are optimizing this process, it means that you are minimizing that what you expend, that you are maximizing what you gain. So minimizing, for example, refers to using the least amount of water, but maximizing also refers to getting the best product that you can get. Okay, so that's optimization.
So more like efficient.
Efficiency, yes. Optimization, efficiency, yes. Interchangeable words. Okay. Okay. So and to model it, we're going to use an existing model. Okay, an existing model, which is called the Newton's law of cooling. Okay. So it's basically straightforward. It's the rate of temperature change in the product is proportional to some constant, which is called the cooling rate constant, times the product temperature, because it's a higher temperature, minus the room temperature. Remember, the room temperature is about 4 degrees. Okay.
Can you please talk about it again?
Okay. Right. So the way that your product, okay, this here dP dt refers to the cooling of the product, right? It refers to the cooling of the product. So here Tp means the product temperature, and it's changing with time, with respect to time, and it's proportional to some cooling rate constant. So this is just a number, and then in brackets, and you got your product temperature minus your room temperature. Okay. So if you plug the room product temperature and the room temperature, and this here, you would get the cooling rate. Okay. Makes sense? Okay, so we'll come back to what.
And you mentioned first order ODE. What does ODE stand for?
ODE is ordinary differential equation. So what that means is it's only dependent on one independent variable, time. Sometimes physical systems, they can vary with time as well as position. Okay, so. Think about a perfume, right? If you release it here, it's going to be different the concentration of perfume from here is going to be different from here. And as the time goes on, it's also going to change. Okay, right? It's going to be initially high here, but eventually it's going to distribute itself. So it's going to vary. It varies with both position and temperature. Sorry, and time. Okay, makes sense? Okay, and then we basically, next steps to solve the differential equation. First step we do is you separate the variables. Okay, so you take this quantity here to the other side, you divide it by both sides by this. So if you divide by both sides by Tp minus Tr, then here you get 1. They cancel each other out, and here you get 1 over Tp Tr. Okay. Next step is you integrate it. Okay. So then here you integrate it with respect to the product temperature, and here you integrate it with respect to time.
Well, this is confusing. Integration. Why are we integrating in the first place? That's
because we need. You see, this here, the differential equation we started with. This is not a solution.
okay.
Okay, that's just that we stated the problem. That's the equation which describes the problem. But now we need the solution. We need to solve the equation.
Okay.
Okay.
So integration help us solve that equation.
Yes.
Okay.
Yes. This is the method of solving differential equations. Okay. And you get that. Okay, after you integrate it. And then you using your logarithmic properties. You see we've got log here, we've got log here. So we can, using the log properties, we can rewrite this form into this form.
Why we take log?
Oh, if you take the integral of 1 over Tp minus Tr, it's the log. You get log. That's an integration rule. It's not something I made. It's just something.
Yeah.
So
Sure.
if it's in factor forms, like in fraction numbers, like 1 over something, it's in fractions.
Yes. So
for fractional numbers, we take log.
So if you were integrating, for example, 1/4.
Yeah.
So because it's a constant, you can actually take it outside the integral. Okay.
So if it was one whole number, then no need of taking log.
No, you can't, because we'll have to take it outside the integral. So but if it was, for example, 1 over x, then it's log x.
Yeah.
Did you have a question? No. Right?
You also ask it.
Okay. Then you.
So just one thing, like you have kind of divided the
It's a log rule.
into a log form, right?
Yes.
So let's say, for example, log natural Tp minus Tr, and then that's one term, and then there is another term.
Yes.
So what does this term mean, and what does that term mean? Like
Okay.
if I have to relate it to your potato cooling example, where are we now in terms of this equation?
Okay, so we're not done yet.
Okay.
Okay, we have to integrate the limits. We have to integrate. We have to do the integration using limits. Okay, so the top limit is the product temperature at any time. Maybe after 5 hours, maybe after 1 hour. Okay, and then the lower so this is called upper integral, and this is called the lower integral, and this is the initial product temperature. Okay, so after it comes out of the chilling water, it's at 25 degrees. So this is what that is. Okay, and then you evaluate the integral of these 2 points. So here T is your product temperature, and T is your product temperature, T is your room temperature, and here log is your product initial temperature minus your room temperature. And if you use your log properties, you get this.
That's impressive. Very good. Now I'm getting along. So
good.
Please keep explaining this way.
Okay, and you get that. Unfortunately, the next step, I did skip a number of steps because I thought it was going to be too long. Okay. Okay.
Let's try.
Okay, so this equation, what we want to do is we want to rearrange for Tp. Okay. And so one of the first steps we do is we take the log on both sides, So we take the anti-log, which is the exponential, right? Okay, and here we get just this fraction, and here we get e, the exponential of this. Okay, and if you do the algebra on this side, then you get this.
Okay, so TP is basically
Yeah. So TP is your product temperature anytime.
Okay, which is a function of.
Which is a function of your room temperature.
Okay.
Which is also a function of your initial product temperature.
Okay.
Which is also a function of your room temperature. Which is also a function of your cooling rate constant. Which is also a function of your time.
Okay.
Right? Because that's going to change with time. Right, Yusuf?
Oh, yeah.
Yes.
Yeah.
Keep going.
Okay. Right? Okay, so that's the equation we saw, right? In the last page, that one. It's just exactly the same. But we've got a K. K, we said it's a cooling rate constant, and it's a unique to each system. So it's unique to apples, it's unique to potatoes, and the only way you can really determine it is by if you do experiments. Okay? And with, okay, this equation is useful. So it came from this one here.
Which one? You indicate on there.
There?
We
The one
don't know.
with the
We
square?
can't see there.
Sorry, not the one with the square?
Yeah.
Okay, sorry. That's right. Okay, so it's this equation. We take this equation and experimental data and we determine K. And this is how we do it. Okay, so notice something unique about this equation, which is that it's actually a linear regression model. Yeah? Basically. So if you plot that versus time, which I do in the next step, okay? So you plot that as your y, which is that, and you go your time as your x, okay? And then you do experiments, and you get 2 points, and you take the slope, and look at the slope, what the slope is. It's K, right? And then, for this, it works out, when I did the math, at 0.04 hours per hour.
No, you have done some experiments to
Yes.
to get that number of K.
Yes. No, because you have to do, because it's for a straight line, how many points do you need? 2, exactly. To draw a straight line, you need a minimum of 2 points, which means you need a minimum of 2 experiments.
Yeah, initial.
Yeah? Yeah. And then you just take the slope of your data and then you give your K. Okay?
One point in time, then another point in time, then the difference.
Yes.
Yeah.
Yes, yes, yes.
That difference over that difference.
Yep. Okay, so that's the equation there. That's the equation there, and then we just put it the number we calculated just now. Okay? And then we plot that as the time varies, right? So these are fixed, right? The room temperature is fixed, the initial product temperature is fixed. Only the thing that varies is time, right? So as we plot, as the time goes on, the product temperature goes down, and it attenuates towards the room temperature. Okay, so say the product temperature that's required is 5 degrees. So say after 3 hours, you want to check whether it has reached 5 degrees. So you just go to your 3 hours and you read across your temperature. It's about 8 degrees, so it's not good enough. Okay? So that's how you use it. So here is its usefulness.
Okay. Why you graph like it's 7 if we look at it horizontally?
Yeah.
At that point, the temperature should drop down to 0.
No.
To 4.
No, it can't even reach 4. It's impossible.
No, like if that graph shows probably the temperature of the potato, right?
Yes.
So at some stage, the temperature of potato is going to be equal to the room temperature.
Yes,
that's
but
what you're assuming.
the room temperature is 4 degrees.
Okay.
It's not 0 degrees. Okay? So it will not reach.
Okay, so we are assuming. Okay, that's
Yes.
good. That's good.
Yeah?
Good answer.
Right? Okay? Alright, so that's how useful it is. Okay, that's mathematical model for you. But in the last problem we saw, we were using an existing model, which was the Newtonian model, which Newton designed. But life is not that easy, and in most likelihood, your system's unique, and therefore there is no existing model to design it, right? To describe it. So what will happen is you have to come up with the equation. Okay, you have to come up with the differential equation, then you have to solve it. Okay, and these are the steps. Part 1 is you state your model purpose. It's just one step. You say, I need to predict this and this. Part 2 is conceptual design. It's about 5 steps. Model formulation, you do actually the calculations. And then analytical solution. Sometimes, if it's possible, then you come up with analytical solution like we did in the last differential equation. Okay? Step 5, you come up with a numerical solution using, for example, MATLAB or Console, something like that. 6, you model validation. You take your numerical solution and you compare it with experimental data to validate it. And the last step is if your validation does not work, i.e. if your model sucks, then you have to improve it. Okay? Now we're just going to quickly go through these steps. Okay? With an example. Okay? So I chose a fermentation tank, a pair of fermentation tanks. Okay, so we've got some product here, we've got some product here. We are heating by the hot water. The hot water is coming through here. It's a coil here and it's moving here. Okay, so step 1 was what? Part 1 was model purpose, and it was only one step. Okay, the model purpose is to predict the temperature in the tank here. Okay, this is what we want to predict. Okay, and this basically that's it. Part 2 is the conceptual design, and the first step is to draw a picture. We've already seen the picture, okay, so there's nothing new there. And then the second step is to provide a process description. You describe the process, see what's happening. Okay, and what's happening is quite simple. Okay, so you've got hot water entering through the coil. Okay, it's given its heat to the product, and it's given as a cold water. Okay, and then the product in here is being recirculated by this pump. So it's being pumped here into this product, into this tank, which is being heated up. And then it comes back. So it's a closed loop here. Yeah. Okay, so that's the process description. And then part 3 is assumptions. Assumptions, without assumptions, your model is basically impossible to do. Okay? Your models, you do your assumptions to simplify it. To simplify with your model. So we had a tank, right? So for example, if you don't make a complete mix in both tanks, then that means each little area of the tank, the concentration or the temperature is going to be different. Therefore, you're going to have to write a specific differential equation for each little section. So the assumption to make is the temperature everywhere in the tank is the same. And if you've got an agitator or a mixer, that's reasonable assumption. So you do many assumptions, but I just listed only a few, okay? So far, so okay?
You're doing best, man.
All right. Okay, next step 4 is the nomenclature for variables. Okay, so you list your variables. So you've got 4 columns. You got your simple, for example, the first one is T for time. You got your description, which is time. You got your units, seconds, and you've got your type, independent variable. Yeah. So it's like X. If you got Y is equal to mx plus C, then it's X your independent variable. Yeah. Okay. Next one is, for example, another variable type is the mass, the fluid of mass in the tank. That's called, so it's in kgs, and it's called a system input. System input is something that you just have to go and measure it. You know, you can't predict how much fluids in your tank without knowing it. You know, we're not exactly measuring how much it is. Another type is dependent variable, which is the opposite of this one. So this is Y. Y depends on X, for example. All right. So this is, and the last one is a consequential variable. So CV variables, which are basically if you know, for example, your dependent variable and your system input variables, then by using algebra, you can calculate this one. Okay, so it's the consequence of knowing these two. Okay. Next step is the number, and then you summarize it. Okay, so if you go through the whole model, because I only listed a few of those variables, but you would get 11 of system input variables, like the mass of the tank. Therefore, you need 11 values. You've got one independent variable, which is the time we saw.
Yeah.
Okay, so you need one ordinary differential equation for that. And you need two differential equations. You have two dependent variables, okay, which is the temperature in both in the two tanks. Okay, and then you got one CV variable, which is the outlet temperature of the cold water. Okay. Next one is, now we start the model formulation. Now we come on, and this is where it gets nitty gritty. This is the good stuff. So the first step is to restate your model purpose. And what we're trying to do, we're trying to model the temperature in this tank. Yep, so that's the tank we're interested in. And then the step 2 is to state your basis. So what are you dealing with? Are you modeling heat transfer? Are you modeling mass transfer? Or are you modeling momentum transfer? Okay? So in this case, we are modeling a heat transfer, and it's steady state. What that means is, with time, the product temperature is changing with time, because it's been heated up, right? If you heat it up for 5 minutes and 10 minutes, 6 minutes, whatever, it's changing with time, so it's unsteady state. Okay? And then you write a word balance. Okay?
Step 3.
Sorry, step 4. Oh, that meant to be step 3 now. Okay? Step 4.
Okay.
Okay? You write the word balance. So you say the rate of heat accumulated in this tank is equal to the rate of heat entering with the incoming water minus the rate of heat exiting in this water, plus the rate of heat going into this tank, and finally plus the rate of heat coming back to this tank. So it's like, saying in this room, the people coming in, the rate of people accumulated in this room, and the people coming in minus the people going out. Right? If 6 people are coming in and 2 people are leaving, then the rate of accumulation is 4. Right? All right. Step 5, which is supposed to be step 4, that you choose units. Okay. So in this case, it's joule. Because we're doing heat transfer, it's joules per second, or you can use calories per second, but generally it's joules per second. Okay. If you do a mass transfer, it's moles per second. If you do a momentum transfer, it's newtons per second. Okay, that's the word. And then you take your word equation that we saw only in the last page, and you convert it to equations. Okay. Okay, right? So it's actually not too bad, because whatever it is.
So simple story, and now.
Huh?
That was a very simple story.
Yeah.
It seems like some third world.
Just tell the story in mathematics way.
Okay. So what this it's a differential equation. So what it's basically saying is the mass in the tank, that tank, times its specific heat capacity, Cp, times the rate of temperature change with time in the tank is equal to rate of heat in, which is the flow rate of fluid coming in with specific heat capacity times this temperature in. Minus what's leaving out, what's leaving with the yellow here, blue arrow, which is the flow rate, specific heat capacity, and temperature. Same thing, what's going out, its flow rate, its specific heat capacity, and its temperature. But the temperature here is the same as the one in the tank. Yeah? And you do what's coming back. The specific heat capacity, flow rate, specific heat capacity times the temperature of tank 2, because that's where it's coming back. Yeah, right? Makes sense. Yeah. Not too bad, right? It looks horrendous to begin with, but it looks not too bad actually. Okay, the next step is you do unit balance, dimensions, okay? Alright? So for example, your mass is kgs, your specific heat capacity is joules per kg per degrees, and your this here, this product here, this component here is your temperature in degrees divided by your seconds. So you can see that kgs cancel with kg, degrees cancel with degree, and you got joules per second. Yeah, and you do this for the same thing. You do for this, and you do for this, and you do for this, and then you are ending up with joules per second. And behold, that's exactly the same as what we chose. Okay? If it's different, that means your equation is wrong, and you need to reformulate it. Okay. Next step. Okay. So this is a CV. You know, this was a consequential variable. Remember I said there are variables that if you know other ones, you can algebraically calculate it. So if you go through the same process, you can work out the equation for this temperature. For the temperature leaving out, the water going out. And you come up with this equation. Okay? Need I explain or?
Yeah, you should explain. How did you work that out? This is.
Oh, you go through this exactly same process.
This is for the second cylinder.
No. Okay, so this is the same tank. This is the tank, right? Yeah. So we've got the water leaving out, right? After it came in right here, it gave heat to the fluid in the tank, and now it's exiting the tank. Yeah? Now we want to calculate, predict, what should the temperature of that be? Okay? And to do that, we do a heat balance, like we did for the other one. So we do a word balance like this, okay? Except this term here is 0, okay? Because it's going to be, this is an steady state problem. This was an unsteady state. The temperature is changing with time, but the next one is not changing with time. So it's 0. Tp dt is 0. Okay? And if you do that, then you come up with this equation. This, the one here. Okay? You come up with that one. And then you just do a bit of algebra. Okay?
Yeah, okay.
Okay.
So we kind of like try to produce like different variables in mathematical form, right?
Yeah. We'll get to that in the discussion a little bit in the end, okay? Okay. And then you rearrange for the temperature out, which is what we're trying to get. Yeah. Right? And then you get this equation. Okay? Yeah. You get that equation. It's just algebra, really nothing too complicated. And then you put your, so what was our original purpose? Right? Was to come up with a mathematical model which can predict the temperature in that tank. Okay? Now we have it. Behold, ladies and gentlemen, here it is.
Oh, this is what we were after.
Yes.
Okay, we got it.
Yeah?
Change of temperature.
Yeah? You see a tank?
Yeah.
So it looks too complicated actually, but it's basically this equation and this equation. So if you replace T out, that one here, that one there, with this equation, and you collect the like terms, then you get this equation.
Yeah, you have put that right there.
Yeah, right?
To,
And then you, yeah, this is a common term. This is a common term for these two as well. Okay? So, nothing too fancy.
yeah.
Nothing
too fancy.
Huh?
Nothing too fancy.
Nothing too fancy. Okay.
So innocent.
Yeah, something innocent. Okay? And understand the equation. Now we need to solve it, right? So this is like Newton's law of cooling, right? How we got that one? When we got Newton's law of cooling, the next step was we solved it analytically, right? We rearranged it, we integrated, and all that, right? That's what we did. Now we need to do the same thing for this one. But what do you notice? It's very ugly. It's too complicated, right? Yeah. Newton's was a very simple one, but this one is too complicated. So therefore, we'll have to solve it numerically. What I mean is, we're just going to use let the computer work it out.
And prove that Newton was a good guy.
Good guy. Yeah.
Make things simple.
Yeah, it was simple. It's a simple stuff,
He
right?
did all this, or later on people did?
Sorry? Oh, you're talking to him. Okay, so the tools we have are MATLAB, which is called also Matrix Laboratory, and Console Multiphysics. Okay, Console Multiphysics is for advanced problems. So the one is mainly for PDEs, partial differential equations, like the Pertine example that I gave you earlier, that vary with both position and time. Okay, so we won't use console, we just use MATLAB. Okay, so this is the numerical solution procedure. First step, choose a language, MATLAB, yay. And then second thing is to implement your code. Go to MATLAB and actually type the code. So this is a small fragment of the code that I wrote. And then you get once you implement the code, then you get your numerical solution. Okay? So as time 0, I think the tank temperature, the product in the tank was about 5 degrees. So then it goes up and it stays at 80. So why does it stay at 80?
Maximum temperature of the hot water.
Yeah, exactly. Yeah, right? So it goes up with time and it takes about 1500 seconds to reach about point. Okay? To heat the fermentation tank. Next step is we check numerical errors. You see, when the computer is solving, when the computer is giving us this answer here, it's actually an approximation. It's not an exact solution. When we did Newton's solution, because we could solve the analytical solutions, that was an exact solution. We knew exactly 100% as well. But this one is an approximation. And then you check how good it is. Okay? So you plot the relative tolerances. Okay? So what that means is you check how good it is by changing your relative tolerance. In MATLAB, when you're doing your calculations, you set your relative tolerance, and you plot the difference. So the biggest error that we had was 0.08 degrees. Is that significant?
No.
No. Right? So what we conclude is that the numerical solution is perfectly acceptable. Okay?
So we call this estimation of the model?
Yes. Yes, it's an estimation, but it's off by about 0.08.
Yeah.
Which is perfectly acceptable.
So in a say econometric model or any regression model,
yeah,
and we say E error term.
Yes.
So this 0.08 is that E.
It's similar.
Okay.
Not exactly.
Okay.
Not exactly, but I'll get down to something similar to the end of the presentation of that one.
Right.
Okay. Okay. So we go. The next step is to perform. So when you're doing your MATLAB coding, right? Sometimes you can make mistakes, but MATLAB can still work, and you can actually get erroneous answer, and say, "Oh, it looks fantastic." So you need to check your code, and the way you do it is by comparing it with analytical solution. So you saw that complicated equation. We just bring it down into something much simpler, and then we solve it analytically, like we did Newton's, and we get something like this. And we plot this, the analytical solution, which is this one, versus the numerical solution, what our MATLAB predicts. And you can see that they, can you see from back there?
Yeah.
You can see that they exactly intersect. Yeah? So which that assures us that our code is perfectly okay. Okay? It's good. Okay, and the last is step, well, not the second to last step, part 6, is to validate your model. So you come up with this good model, well, what thought to be a good model, and then you go to the lab, you conduct experiments, and then you compare your mathematical prediction with your experimental findings. Okay, so we've got the red, or we've got the blue one, which is your numerical solution, what MATLAB predicted, and you got your experimental prediction. Okay, and look, here's, I think this is what you were talking about, brother. Your R squared is 99.999%. Yeah, so that tells us the difference is very, very small. Yeah, difference is very, very small. Therefore, our model is really good. And that's why it looks very complicated, right? To account all the changes. If it was a very simple one, then this would be much longer. Okay, and therefore the next step, if our model was not was not this good, then we would have to go back to the process and improve it. Okay, but now since it's good, then we can use it. Okay, that means the predictions of our model are acceptable and they are accurate. Therefore, we can use them. Okay, there you go, and that's mathematical modeling for you. All right, just switch on the lights. Any questions, Rashad?
Well, when is the next lecture?
The next lecture will be on if you are keen to have one particular if there is here.